Let's look at some examples where we are going to solve an exact differential equation or initial value problem. On the left, I've written down steps that we can follow, and on the right, I've written down the general form for an exact differential equation with the exactness condition. We'll go through these steps one by one as we work through each example. Let's look at our first example. The first thing that we're going to do is we're going to find m and n and then check if the exactness condition holds. We're going to let m of xy be the function that multiplies dx, so that's just 2xy minus 3x squared. And then we're going to let n of xy be the function that multiplies dy, and that is x squared plus 2y. Now let's see if this equation is an exact differential equation. We're going to take the partial of m with respect to y. That is going to be 2x. And then over here on the right, we're going to take the partial of n with respect to x, and that is 2x. Notice that these two quantities are equal, so that tells us that we have an exact differential equation, and we can go ahead and go on to step 2. In step 2, we're going to let the partial derivative of a function f is going to be our solution, with respect to x equal m of xy, and that is equal to 2xy minus 3x squared. We're going to do the same thing with respect to y. We're going to take the partial of f with respect to y, and we're going to let that be equal to n of xy, and that was equal to x squared plus 2y. We're going to save this for later, and now we're going to work with the partial derivative of f with respect to x. Let's go ahead and rewrite that function. We have the partial derivative of f with respect to x is equal to 2xy minus 3x squared. We want to get f by itself, so we are going to integrate each side of the equation with respect to x. We have the integral of the partial derivative of f with respect to x times dx, and then we integrate our right-hand side with respect to x. So we have 2xy minus 3x squared dx. On the left, we just get f of x and y. And then on the right, we have, let's see, we're integrating with respect to x, so we get x squared y minus x cubed. And then we have to add on an arbitrary constant, but we have to be careful. Our arbitrary constant is not going to be c, it is going to be a function of y, because f is a function of both x and y. I'm going to highlight g of y because that's what we want to find now. And we're going to do that in steps 4 and 5. In step 4, we're going to take the partial derivative of f with respect to y. This gives us x squared plus g prime of y. Now we're going to go back up to step 2 because step 2 gave us the partial derivative of f with respect to y, and this is x squared plus 2y. So you can see from this, we can find out what g prime is. Our g prime is just 2y. So we have g prime of y is equal to 2y. Now we need to find g of y, that's highlighted in green. So to do that, we are going to integrate both sides of our equation with respect to y. On the left, we just pick up g of y, and then on the right, we have y squared, and then we're going to add on an arbitrary constant c1. In step 6, we are going to substitute this expression that we just found for g of y back up into f from step 3. This gives us f of xy is equal to x squared y minus x cubed plus y squared plus c1. The solution to an exact differential equation is that our function f is equal to an arbitrary constant that I'm going to call c2. The reason I'm doing that is we can now combine c1 and c2. We can say x squared y minus x cubed plus y squared is equal to c2 minus c1. We'll then combine these constants and we'll get the final answer, x squared y minus x cubed plus y squared is equal to an arbitrary constant c. And that's the implicit solution to the differential equation. Let's now look at our second example. I wanted to do this example because I wanted to show you how solving an exact differential equation works when you have what's called an initial value problem. Our first step is to let our function m of xy be the function that multiplies dx, and that is y cosine x plus 2x e to the y. And then we're going to let n of xy be the function that multiplies dy, and that is sine x plus x squared e to the y minus 1. Now we're going to check if this is an exact differential equation. We're going to calculate the partial derivative of m with respect to y. This gives us cosine x plus 2x e to the y. And then over here on the right, we're going to take the partial derivative of n with respect to x, and that is cosine x plus 2x e to the y. The partial derivative of m with respect to y is equal to the partial derivative of n with respect to x, so our equation is exact and we can go ahead and solve it. We're going to start by setting the partial derivative of f with respect to x equal to m of xy. And that is equal to y cosine x plus 2x e to the y. Then we're going to set the partial derivative of f with respect to y equal n of xy, which we found to be sine x plus x squared e to the y minus 1. Let's just make a note that we are going to save this one for later. And in step 3, we are going to work with the partial derivative of f with respect to x is equal to y cosine x plus 2x e to the y. We are going to integrate each side with respect to x. So we have y cosine x plus 2x e to the y times dx. On the left, we get our function f of xy. And then on the right, we are integrating with respect to x. So we get y times sine x plus x squared e to the y plus our arbitrary constant g of y. G of y now is what we want to find. To find g of y, in step 4, we're going to take the partial derivative of f from step 3 with respect to y. We are taking the partial derivative of this function with respect to y. This gives us sine x plus x squared e to the y plus g prime of y. The partial derivative of f with respect to y is what we had saved. So we're going to now bring this down, and we're going to set this equal to sine x plus x squared e to the y minus 1. Looking at this, you can see that g prime of y now is equal to minus 1. In step 5, we are going to find g of y. So let's write down g prime of y is equal to minus 1. To find g of y, we are going to integrate both sides of this equation with respect to y. On the left, we get g of y, and then on the right, we get minus y plus an arbitrary constant that we'll call c1. We now have g of y, and we can substitute it back in to our equation for f back in step 3. Let's take this and bring it down here. And this gives us our step 6. We have f of xy is equal to y sine x plus x squared e to the y. And now we're going to add in g of y. And that's minus y plus c1. Now we're going to go ahead in step 7 and find our final solution. We are going to take f of xy that we just found in step 6, y sine x plus x squared e to the y minus y plus c1, and we're going to let that equal an arbitrary constant because that's the solution to an exact equation. Let's now combine these constants. Let's let c be c2 minus c1, and we can rewrite this as y sine x plus x squared e to the y minus y is equal to c. In this problem, we have an initial value problem. We were given that y of 0 is equal to 2. That means that when x is equal to 0, y is equal to 2. We're going to take this equation right here, and we're going to substitute in both of those values. This gives us 2 times sine of 0 plus 0 squared times e squared minus 2 is equal to c. And we need to find c. Sine of 0 is 0. Our next term is 0. So this just gives us that c is equal to minus 2. We're going to take this expression now, and we're going to let c be equal to minus 2. This gives us y sine x plus x squared e to the y minus y is equal to minus 2. Our answer is going to be a lot nicer if we actually pull the minus 2 over to the left. So I'm going to write our final answer as y sine x plus x squared e to the y minus y plus 2 is equal to 0. And there's the solution to our differential equation written in explicit form. Let's now look at example 3. This example is different, but I wanted to include this in case you encounter a problem like this. We want to find the value of k, here's k right down here, so that this differential equation that we've been given is an exact differential equation. To do this, we need to make sure that the exactness condition is satisfied. So let's start by assigning m of xy to the expression that multiplies dx, and that's 2xy squared plus y e to the x. And then we're going to let n of xy, just like we did when we solved our exact equations, that is going to be the expression that multiplies dy. Now we're going to choose k so that our exactness condition is satisfied. Our exactness condition is the partial derivative of m with respect to y is equal to the partial derivative of n with respect to x. Let's calculate those partials. The partial derivative of m with respect to y is 4xy plus e to the x. And then the partial derivative of n with respect to x is 4xy plus k e to the x. we need to make sure that these two sides of the equation are the same. They are going to be the same if k is equal to 1. So our solution is k is equal to 1. And that's it. You now know how to solve exact differential equations, and you should be all set to work through some examples on your own.
If this video has been helpful to you, please consider subscribing to my channel. Keep believing in yourself and have a great rest of your day.